We are going to start Module 2 of Chapter 4. In this module, we shall discuss the Hamiltonian of a dynamical system. So far, we have discussed the Lagrangian mechanics, a reformulation of classical mechanics which is known as Hamiltonian mechanics will be discussed in this module. Hamiltonian has been developed with the help of Lagrangian. An Irish mathematician, W.R. Hamilton, developed this dynamics in 1833. In this module, we shall discuss the detail about it. The learning objectives of this module are: conservation of angular momentum. We shall discuss this theorem. Legendre dual transformation will be discussed in this module. Using Legendre dual transformation, we shall define the Hamiltonian of a dynamical system. Now, we shall discuss the conservation theorem for angular momentum. Angular momentum is defined as the moment of a linear momentum. Let Qj be a cyclic coordinate. Then Qj will be absent from the Lagrangian. Therefore, delta Qj corresponds to a rotation of the system of particles around some axis if Qj be a cyclic coordinate corresponding to rotation. Let the system be conservative. In such cases, sum of kinetic energy and potential energy remain conserved, that is fixed. Then the potential energy capital V depends on position only. It is well known that kinetic energy T is equal to half into mass into velocity square. So, kinetic energy T depends on translational velocities which are not affected by rotation. As the position coordinate Qj is affected by rotation delta Qj, so the kinetic energy T does not depend on the coordinate Qj. As capital V is independent of velocity Qj dot, so we have del capital V del Qj dot equal to 0, and as capital T is unaffected by the rotational coordinate Qj, so del capital T del Qj equal to 0. Now, Lagrange's equation of motion corresponding to the generalized coordinate Qj gives ddt of del capital T del Qj dot minus del capital T del Qj equal to minus del capital V del Qj. If we use the relation del capital V del Qj dot equal to 0 given by 4.10, in the equation 4.11 we have ddt of del Qj dot operated on T minus V equal to minus del capital V del Qj. This can be written as ddt of del capital L del Qj dot equal to minus del V del Qj. Please note that in a system, Lagrangian can be written as the difference between the kinetic energy and the potential energy if there are holonomic constants. This equation can be written as ddt of Pj equal to minus del capital V del Qj. Pj is the generalized momenta. Thus, we have Pj dot equal to capital Qj, where capital Qj is the generalized force associated with the generalized coordinate Qj and given by capital Qj equal to minus del capital V del Qj. As Qj is a rotational coordinate, so Pj is the component of the total angular momentum along the axis of rotation. The magnitude of change in the position vector Ri vector due to the change in rotational coordinate Qj is absolute value of delta Ri vector equal to Ri vector into sin theta into delta Qj. This gives absolute value of del Ri vector del Qj equal to Ri vector into sin theta. Now, del Ri vector del Qj is perpendicular to both Ri vector and n vector. Ri vector is the position vector, whereas n vector is the unit vector which has been considered along the axis of rotation. Therefore, del Ri vector del Qj equals to n vector cross product with Ri vector. Now, Pj equal to del Qj dot of capital T. T is the kinetic energy, Qj dot is the generalized velocity, Pj is the momentum. Therefore, Pj equal to summation over I mi Vi vector dot del Ri vector del Qj. If we put the value of del Ri vector del Qj in this relation, then we get Pj equal to summation over I mi Vi vector dot n vector cross Ri vector. This can be written as Pj equals to n vector dot summation over I Li vector equals to n vector dot capital L vector, where L vector equals to summation over I Li vector, which is the angular momentum of the system. Therefore, L vector equal to summation over I mi Vi vector cross Ri vector. We have already mentioned that L vector is the angular momentum vector, which is nothing but the moment of linear momentum. Here mi Vi vector is the linear momentum. Therefore, L vector is the total angular momentum along the axis of rotation. It is known that if Qj is cyclic, then the generalized momentum Pj is constant. Hence, one can conclude that if the rotational coordinate is cyclic, the component of total angular momentum along the axis of rotation remains constant. If a rotation coordinate is cyclic, then the system remains invariant under rotation. In this case, the angular momentum remains conserved. So, one can say that conservation of momentum is closely associated with the symmetry property of a dynamical system. If the system becomes spherically symmetric, then the angular momentum components are also conserved. Now we shall discuss Legendre dual transformation, which is very important in this chapter. For generating a new pair of independent variables x and z from an initial pair x and y, Legendre transformation is a standard technique. Please note that first coordinate is fixed, only the second coordinate has been changed here. The transformation is completely invertible. That is, applying the transformation twice, one can get the initial pair of variables x, y. If L, the Lagrangian of the system, is defined as L equal to L function of generalized coordinate qk, generalized velocity qk dot and time t, then we have pk equal to del del qk dot of L, k varying from 1, 2 up to n. Here pk is the generalized momenta, L is the Lagrangian, qk dot is the generalized velocity. If one wants to eliminate the generalized velocity qk dot in terms of generalized momenta pk, then this elimination considers Lagrangian as a function of qk and del L del qk dot with time. The transformation which does this mathematically is known as Legendre transformation. So, Legendre transformation helps us to obtain Lagrangian in terms of generalized coordinate, generalized momenta and time. Now we shall discuss an important theorem. Let a function capital F, function of x1, x2 up to xn, has an explicit dependence on the n independent variables given by x1, x2 up to xn. Let the function capital F be transformed to another function capital G, function of y1, y2 up to yn, which is expressed explicitly in terms of new set of n independent variables y1, y2 up to yn. These new variables are connected by the old variables by a relation which is given by yi equal to del del xi of capital F. Here I vary from 1, 2 up to n, and the form of capital G is given by capital G function of y1, y2 up to yn equals to summation I equal to 1 to n xi into yi minus capital F x1, x2 up to xn. Then the variables x1, x2 up to xn satisfy the dual transformations. That is, the variables x1, x2 up to xn satisfy the relations xi equal to del capital G del yi for I equal to 1, 2 up to n, and capital F, which is a function of x1, x2 up to xn, equals to summation I equal to 1 to n xi into yi minus capital G function of y1, y2 up to yn. The transformation between the two set of variables x1, x2 up to xn and y1, y2 up to yn given by the equations 4.13 and 4.15 are known as Legendre dual transformations. Now we shall prove the result. It is given that capital G function of y1, y2 up to yn equals to summation I equal to 1 to n xi into yi minus capital F, which is a function of x1, x2 up to xn. Then if we take the variations, then we get delta capital G equals to summation I equal to 1 to n del capital G del yi into delta yi. Again, delta G can be written as delta G equals to summation I equal to 1 to n xi into delta yi plus summation I equal to 1 to n yi into delta xi minus summation I equal to 1 to n del capital F del xi into delta xi. We have taken the variation given in the first equation. Thus, we have summation I equal to 1 to n del G del yi delta yi equal to summation I equal to 1 to n xi into delta yi plus summation I equal to 1 to n yi into delta xi minus summation I equal to 1 to n del capital F del xi into delta xi, since both the variations are equal. Combining these, we get summation I equal to 1 to n del G del yi delta yi equals to summation I equal to 1 to n xi into delta yi plus summation I equal to 1 to n yi minus del capital F del xi into delta xi. Since it is given that yi equal to del capital F del xi for I equal to 1, 2 up to n, and as delta yi's are arbitrary, since yi's are independent coordinates, so we have xi equal to del del yi of capital G. This result holds for I equal to 1, 2 up to n. This proves the duality of the transformations. Relation 4.16 can simply be obtained by rearranging the terms given in the relation 4.14. Moreover, starting from the relation 4.15, one can easily prove the relation 4.13 exactly in the same fashion, in the same way. Now, we are going to define Hamiltonian of a system with the help of Legendre dual transformations. In Lagrangian mechanics, generalized coordinate qk, generalized velocity qk dot are taken as the Lagrangian variables with time t as a parameter. In Hamiltonian mechanics, the basic variables are the generalized coordinates qk and the generalized momenta pk, where k varies from 1 to up to n. We define the generalized momenta pk as pk equal to del L del qk dot for k equal to 1, 2 up to n. Here L is the Lagrangian of the dynamical system. Let us now define a new function capital H known as Hamiltonian function by the relation capital H equal to summation k equal to 1 to n qk dot into pk minus capital L. Thus, capital H is a function of qk dot pk, where L is the function of generalized coordinate qk, generalized velocity qk dot and time t. L is the Lagrangian of the system. With the help of 4.17, qk dots can be eliminated from the right hand side of 4.18, which can then be expressed in terms of generalized coordinate qk, generalized momenta pk and t. In Hamiltonian H, t comes from Lagrangian L, as L depends on time t. So, capital H equals to capital H function of generalized coordinate qk, generalized momenta pk and time t. In this module, we have discussed the conservation of angular momentum. It has been shown that it is closely associated with the symmetry properties of a dynamical system. Moreover, the Legendre dual transformation has been discussed in detail. Hamiltonian, a new function, has been defined in terms of this transformation. It helps to reformulate the classical mechanics, which is known as Hamiltonian mechanics.